And this is trying to get some insight in what this learning principle of backpropagation actually doing. It is what in these neural network programs, if you have a very sophisticated program like Mathematica, or you do it in Python or C++ or in Keras or in Caffe, you name it. In Mathematica it's called nettrain. That's a wonderful command, and it does a lot. It takes the output, checks the cost function, the error, and updates all the filters. And you take it for granted because it's wonderful, it works, you don't have to look at what it does, but let's have a little bit of a look under the hood, what's actually happening in this backpropagation. So what I like to do is to first make a forward pass and then make a backward pass. This is actually done millions of times. And do this on a very simple numerical example. It gets so complicated that I go not in the very tiny, tiny details. You can read it one by one. There's a beautiful website. Actually, I took this from a website, and you can study this, take your own numerical examples, but I give you the principle here. And the network today is quite big. You see the classical AlexNet here. And you can easily calculate how many weights do I have, so many filters. So you start with 11 by 11 filters, and here you have a stack. It's a tensor of 48 different filters. You do pooling. You have different types of convolutions after each other. You have nonlinearities, and we're going to see what is the propagation of these networks. We know convolution, but how does it work if we go backwards? We know that we go to a minimum of the error, so we have gradient descent. Well, we need derivatives. If you need a gradient descent, what kind of derivatives? So let's have a little bit look under the hood. So we have a forward pass with all these layers. You can now program these layers one by one, and I really invite you to do that. We can look after in the afternoon. In Mathematica, it's extremely simple, but in most languages, it's simple. You just say convolution layer, ReLU layer, softmax layer, all these layers, and you stack them as you like. You can make 100 layers, you can make 15 layers, whatever. You can take filters at all sizes. And once you have the topology, you let the weights fill in. You start with random weights, and this filling in process is done by this error backpropagation. So how does it actually work? We take a simple numerical example of backpropagation from a random network. And this is from a very nice medium.com article. I really can recommend you to read medium.com. It has a very nice artificial intelligence section with beautiful tutorials all over the place. So many people, they write their own learning process. And they say, hey, I studied this course. I didn't understand it, but let me summarize it. And they give a very nice blog. And if you start reading these blogs, it's a very quick way in an easy, understandable language to get up to date. And there are hundreds of blogs every day, so you can pick out whatever you like. OK, so what do we see? Input layer of just 3 neurons. And we have a ReLU layer. So that's a rectifying linear unit. If it's negative, it becomes 0. And if it's positive, it is the identity. We have a sigmoid layer. And we have a softmax layer. And all these layers, they do something mathematically. This is the simplest one. That's actually kind of a threshold. And we have weights. We call this I1, J1, K1, and L1. So we have here the weight from I1 to J1. That's this weight. This is from I1 to J2. And all these weights have numbers, and very easy to see all these numbers. And we're going to calculate these weights. Quite a number of weights. Let's see how we actually do that. So you build a neural network first, and that's actually always the way you start. You begin with the architecture. If you don't know the architecture, take a template from some other papers. You say, OK, this is more or less working, and then you start modifying that. But you say, I define the number of layers, size of the filters, etc. And then you initialize the weights and the biases. So all these weights, you see, I1, J1, I1, J2. So all the weights from this layer here to the other weights are way ij from 1 to 2, it's a matrix. And the matrix is filled in with random numbers. That's how we start. And we take an input vector, 0.1, 0.2, 0.7. It's also chosen here more or less random, but we're going to see what does this input do on the network. How does it propagate? So we have these layers, 3 layers before the output, 3 matrices. And we first go make a forward pass, then we get an error, and then we go calculate the backward pass. So, and during the backward pass, we adjust all the biases and the weights. So let's have a look at this first forward pass in this layer 1. So we're going to look at, this is layer 1, H1, layer 2, and the output. We have an input here and an output, input 1, output 1, input 1, output 1. So what is the mathematical formulation? This is a vector as input. This is the weight matrix. You add the bias, and you get an output. Sorry. The Rayleigh operation, which is done here, is a mathematical operation. And how does that actually look like? Maximum of 0 and x. That's the formulation. If you program it, it's an easy way. If you put in -1, you get 0. If you put in 4, you get 4. So that's a very simple operation. We're going to do the same for a sigmoid operation, for a softmax operation. These are just mathematical operations. So now we have the Rayleigh operation. So if we see this H1, out 1, out 2, and out 3 is actually the maximum of H1 in, H1, 2, and H1 in 3. So this is the formula here. If we do this now with our numerical examples, we have the input vector, we have the matrix, the bias was not chosen randomly, but just put on 1, and then we get this as output. Here we do the Rayleigh operation, and it remains the same. And this is my triple vector, and that's my input for the next layer. So you calculate layer by layer, and this is actually what all these GPUs are doing with your millions of input data, much bigger vectors than just 3. So let's take the next layer, and that's the sigmoid layer. So we have now H2 in 1 to out 1, here in 2 to out 2, etc. So we have the same. So what do we do? We have the same input vector times the weight matrix plus the biases is the output vector. But now we have a sigmoid operation, and the sigmoid operation is this S-shaped curve, and it's represented by 1 over 1 plus e to the minus x. You have different variations for sigmoids. You have also the tangent hyperbolic, and there are many ways. Pick your choice, but this is an easy one. So if you say, well, what is this sigmoid function doing? It works on this h2 out 1. So you put here in x, you get 1 divided by 1 plus e to the minus h2 in 1, and this one and this one. So if you now do this numerically, this was the vector we calculated from the previous layer. So we have these 3. We now put in the matrix of weights from the second layer, the biases, and we get this as output. And now we do the sigmoid function, and this triple is now the output from my second layer. Actually, you can do this step by step. Let's take one more, and that's the softmax layer. Well, the softmax function is a normalized exponential function. I took this from Wikipedia. It is very nicely illustrated in this simple figure. If you have a triple vector here, you want to break them down into probabilities which add to 1, because the utmost probability that if you have all chances together, it is 1. It makes it sure. Well, there's a formula that you say, I take the exponential of a particular item, like 0.1, and I sum them by the sum I divide them by the sum of these exponentials. Because it's exponential, I turn them into probabilities weights, and now you get 0.7, 0.2, and 0.1, which is the weighted sum that added up to 1. So that's a nice way. It is just a very simple exponential formula. And you make now your vectors into probabilities that add to 1. So here we go. We take now the output from the second layer. We have our weight matrix, the biases, and we get the output here. But now the function is a softmax function. So e to the power of my item divided by the sum of my exponentials. So you put them in here, you have them. And now numerically, this was the output of my previous stage. This is my random initialized matrix that I have here, my biases, and this is the output. So now I have the output here. So with this output, you now have to say, well, we got this, but it should be 1, 0, 0. So I'll make an error. But how can you make an error if you have a matrix of points and another matrix of points? You have to make some definition on how to define this error. And there are many ways to define the error. And the most, or a very popular one, is the cross entropy. And the cross entropy is actually the sum of the weighted logarithms. So if you say I have the logarithm of, I think I have a, here is the cross entropy. It's a very nice reading in Wikipedia. This is the formula you should actually remember. So if you have the entropy between two vectors, P and Q, you say it's actually the sum of P times the log of Q. So that's the number that you get with a minus sign. So this is the standard definition of entropy, but now you have a cross entropy that is two probability distributions with the same underlying set of events. What is the average number of bits you need to represent one channel over the other channels? That's a cross entropy. So if you calculate that formula and you plug in the numbers, you get an error, 2.6. And with that error, we now have to go backwards. So now we're done with the forward pass. We know the error. And now let's see, can we use this error to adjust the weights so this error goes to 0? That's what I need to do. How can I do that? Do all of you know this? Are you programming this already? Because it's redundant if you all know and I go tell you this. But it is actually the essential trick behind the deep neural network. And this was the main trick that these famous guys in this Nature paper came up with, that say, okay, we now understand this backpropagation. And what is actually happening that you say, well, we have an output, and the output is a sum of a concatenated action. So we have an input here, then there is some action here, some function, and another function, and we have weights in between. And if you see, well, this action here, this output, you can write it as this function. So we have W1 times the input right here. It acts on this function. You multiply with W2. Then you have the activity function again. You multiply with W3. So you see a function of a function of a function of a function. So it's the concatenation of a function. So if I want to see how much is this guy changing when I change this a little bit, because that's what I want to see. If I reduce my error a little bit and I say, well, how much do I need to change this to get a change here in the output? I can change it up or down. I can go in any direction. But I like to know this derivative, this sensitivity function. So a change in my weight, how much does it change in? If it goes like this, if I make this higher, my error gets lower, I'm fine. It can also be like this. I need to go this down, then, but this should go down. Well, this should go down to a minimum. So I always want to go this down, not to go up, because I want the minimum error. Well, this sensitivity, and that's the gradient descent property. So you first go find a little bit of tiny motions and see, okay, when is it going down? And not going up. And then you have already, you go in the right direction. So we need to find the derivative. But if you have the derivative here and you want to find it to W1, you first have to find the derivative to here. And then you have to find this derivative relative to this one, and then this derivative relative to that one. That turns out to be the chain rule. So you have a concatenation of functions. If you take the derivative of this concatenation of functions, you know from differential calculus that you take the... So this gradient descent means I only have to calculate a couple of small changes here, and then I know what is the slope in the downgoing direction. I don't need to find this whole field with all these slopes, because if I calculate the whole valley, that's ridiculous. I only have to find a couple of points here, and then I say, okay, now I know this is the gradient. And then I take the next one and so on. So that's far faster. So you calculate the gradient of the delta loss, delta W. So how much is my loss changing if I change the weight? And that's the critical part. You want the loss changing to be negative. And finally, at the end, you want it to be 0. And there are very clever steps in this gradient descent that in the beginning you make big jumps here, but it gets smaller and smaller. And if you are here, there's no change at all. So you have the problem of you make no change. So the learning rate, and this is how you update the weights. You say, I update the weight by starting with my original weight, and I subtract my slope to go further down to my 0 point. And this is called the learning rate, how much you subtract it. In the beginning, you take a learning rate that is, let's say, not too small, but here you want to have a little bit bigger steps, so here you can adaptively change the learning rate while you go down. So a simple, if your error is, let's say, some quadratic function, and the error could be any kind of a representation, but it is a kind of a valley-shaped function. So you have P, that is the predicted value, and A is actual. So the prediction minus the actual value, and you square it, if that is a model for the error. If you have how sensitive is this for the predicted value change, you take the derivative to P. Well, the derivative to P is P minus A. This 2 gets with the 1/2. And you have all kind of derivatives in deep learning that people need to know for the different layers. So if you have a sigmoid function, well, take the derivative of this sigmoid function, you get this one. All you can do in Mathematica, you take it from books or you calculate it yourself. It turns out that you can replace this by the function itself times 1 minus sigmoid. That's sometimes easier to calculate because you have already this function. 1 minus is easy, so you don't need to calculate all these e powers here. The ReLU function has a derivative, and the softmax function has a derivative. So these are all known by the network and used in this chain rule. And now you see that if you have an error here, you want to distribute it over these weights, but these are distributed over these weights, and these are distributed over these weights. So if you write it mathematically, you want to see that the change of the error, when I change this weight 1ij, and this is 1ij, that's in the front of my network. It's not directly here, but it is in the front. So I have to find out what is the derivative. And now you have to say, okay, I do the first step. J is my output from my, let's say, fully connected layer here. So I take dj, dw. But you can say, well, I have actually the chain rule, so that is dj, dp, dp, dw. So I first go past this one. You take the derivative to p, p1 minus a. So now you get the dj, dw1 is p minus a times dp, dw. You can do this layer by layer. So each time you add a new layer and you take the derivative of that layer, and you take the derivative included. And if you do this in the very end, you say, okay, now I see that the derivative to my very first layer is this term times, and now I have here the derivative which included my third layer matrix, and here my second layer matrix. So the more layers you have, this becomes a very long concatenated chain. And then you repeat, and you update this, multiply it with the learning rate to adjust your weights till the error gets smaller, and you update this until the derivative is 0 and you are in the minimum. So that's actually the whole thing. You can read this in great detail. You can numerically exercise with this, make a very tiny program in C, Python, MATLAB, whatever, and exercise, can I really understand this, what happens? And the notebook I show you here gives the very tiny exact details, and you can just play with it. But now you have an idea what these networks underwater really do. It's a lot of calculations, and that's why we need all these GPUs. It's very boring. You have to see it once, and now you see what NetTrain is doing. You never do this by hand, but you have to see a little bit, get of a feeling what's happening actually. You progress through these functions, and you go backwards, and you say, okay, how sensitive through these functions is a very tiny change in the weights so I can get a lower error. And this run, you run this millions of times. Okay, if you want to go deeper reading, these are very nice blogs from a guy called Eli, and I found them very instructive, and in just 15 minutes you have a very good feeling of what's happening here. Any questions so far? Then I have a second part, then we go more, and that's on face detection. So how important is face detection? Well, it turns out that in our brain, face detection is so important that we have dedicated pathways for face detection. It's amazing. We are really face processing machines. Faces are far more important than anything else, it seems. So what people are doing now in monkeys, they find these face pathways, put needles in there, do optical methods, and from the face pathway we know a lot. And I'll show you a little bit of it. And next week we go into some, more not completely, let's say, finished areas, but ideas on how can we learn from the brain and get new ideas from vision. We will see some of these ideas coming back. Well, face recognition is everywhere today. It's on your smartphone, it's on your digital camera, you get the bounding box, you get these faces, and how is it actually working? And it should be simple because it works on your smartphone, and it works on your Sony digital camera. And how can you find a bounding box of a face? It is in every tagging, from Facebook, you name it, and if you look at the Facebook paper, this is a quite nice paper that was published in, when was it, 2014? Deep Face, Closing the Gap to Human-Level Performance in Face Verification. This was a very deep network, 120 million parameters, but they get 97.35%. And that's amazing. That is really good. Humans are almost, maybe not yet that good. This was measured on a famous data set. You should see that. It's called Labeled Faces in the Wild. Let's have a look at Labeled Faces in the Wild. It's a big database, and if you want to play, download it, and you get an incredible amount of these faces. And why is it called In the Wild? Let's have a look at images. Well, this is part of the database. And in the wild means it's not taken frontal in a nice setting, but it is taken from video, from television movies, from whatever. So they come in all kinds of different poses. Some of them are in the shade. People have glasses. People are looking upwards. That's in the wild. So that means pretty tough challenge to find them. So we go see in a minute that you need to find a face independent of its orientation. So we have to do some affine transformation on these faces. We have to find some characteristics in these faces, so some key points. We have to be invariant for intensity. We all see a face here. For our eyes, it's very easy. And why is for a computer so incredibly difficult? Because all the intensities here are different. So we need to be invariant for intensities. Okay, this is in the wild. I took this from a very nice blog, Machine Learning is Fun, and they have a couple of these examples, and I invite you to have a look. We try to build a face recognition system from scratch, very simple, but we take a difficult challenge. We're going to see if we can find the difference between these two famous similar faces. These are both completely different persons. One is a famous actor, and the other is a famous rock musician. And you see the faces are quite alike, but they're all also different. And can our deep learning network see the differences? We can think of what are these differences then, and then you start to design features. Well, we're going to learn the features, and then we see what is being learned. These guys are, in the United States, quite famous, and they even showed up in a television show. And the guy who was leading the show, he was often mixing the two guys intermediate, and they also played a game that they said they were different. But you see the faces are quite the same. We need to build a pipeline, and we go step by step look at these pipelines. So what's the pipeline? Let's look at the movie again. We first find the face in the image. Oops. So we find the bounding box. Then we need to find the features. We rotate and stretch, and we compare against a whole database of known faces. Is my face right there? This is a very common application because many security applications, you want to have, let's say, only those 20 people have access to this gate, show your face, and the gate opens only when you are one of these 20. So first of all, find the face in the image. Anyone an idea how to find the face in these millions of pixels? You could do template matching, but it's quite difficult because the template, how big should it be? You have to do it with lots of templates. What's the orientation? Yeah, there are so many templates. You can only hope that it is more or less working. Turns out that people have done some other ways. This works, as we know, everywhere. You're all familiar with this. It works real time. If you move this in your image, you do this 25 images per second. So it should be fast. And it should be done on very simple hardware like your smartphone or this camera. Well, the mainstream was, it started by a very famous paper by Viola and Jones. Have you read this paper? Is anyone working in face recognition? Not. Because if you work in face recognition, you know the Viola-Jones paper. It was a revolution. Before that, it actually didn't work. And this paper is actually nice to read anyway. This is the Wikipedia explanation of the Viola-Jones object detection network. They use extremely simple filters for feature types of feature detection. And these filters were extremely simple blocky filters. And now see what they use. They call them Haar filters. They did not make any relation to differential structure. But do you see how much they like our differential structure filters approximations? So this is the first order derivative in x and in y, the second order, a mixed order derivative. They used them because they were so extremely fast, just 4 convolutions. But now we have a little bit more detail in, hey, what's actually happening? You look at geometry, you look at these second order derivatives. But now a more reliable existence came when this method was invented in 2005. And this is a paper, Histograms of Oriented Gradients for Human Detection, by Dalal and Triggs. And they, for the first time, said, we should not look at pixels or differential structure of these pixels, but we should look at the context of these pixels around it as well. So if I look at the gradient field, I can look at how much are the gradients changing in the pixels around me. I'm standing in the pixel, have 8 neighbors, and with these 8 neighbors, I have a kind of a star with gradients. And this star pattern is the thing they use. So not the pixel itself, but the 8 values of the gradients. So they made a kind of a local tensor in every point. And that star pattern, think what happens if you have a gradient. Suppose the sun is shining, or you get a shadow, and the intensity changes. These gradients do not change. They stick to your pattern. So you have a very nice intensity invariant thing. You can even look at it rotates with the figure when you rotate it, so it is stuck to the figure. It is an intrinsic geometry thing, not extrinsic, so it is located like our gauge coordinates. It turns out to be a very stable thing. Let's look at this paper. So if I take this paper, histogram of oriented gradients, and I go to Google Scholar, and I type in Google Scholar, can I find this paper? Yes, here it is. And here we see that it is cited by 24,705 papers. That's pretty amazing. This means it is really working so well that everybody is using it and say, okay, I refer to this paper. If your paper gets cited like this, call me and say, hey, you are really famous. This almost never happened. I started last year to do something interesting. I said, let's read the most cited papers in computer vision, and let's read the most cited paper in biology, all these optical measurements. And I found some very intriguing similarities. They have found these cells in the retina as well. These stellate emigrant cells with all these gradient detectors at the boundary. What do you think they do? People don't know yet. And if you see this, and if you see that, and these are very interesting things I want you to use in your next coming career to say, hey, that might be quite interesting. This is such success. This was found by accident, by heuristics. Of course, there was some nice thinking about it. They have never thought about, could biology do the same? And now we have the time that this is starting to become possible. You say, hey, we have a model for biology, we have a model for what happened. But anyway, this time number of cited is amazing and very interesting. So 24,000 times. And if you look next week, it is already increased. So let's have a look how that works on this image. It's actually quite simple. You start in every pixel to look at the pixels surrounding you. So you have this little star. You can make the star 8 or 4 values. And then you measure in that star the gradient direction. And we can do the gradient direction with our Gaussian derivative, and we immediately have it. You take Lx, Ly, and you have the gradient. You take Pythagoras. You can approximate the gradient by just taking the difference of 2 pixels. It more or less all works. But now we only consider the direction that the brightness changes. So dark and bright images will have exactly the same representation. So even if you change the intensity, you go from bright to medium, you get the same gradient pattern. And now, if you see what happens, this is the low resolution histogram of gradient representation from this image. So we don't need to do this at every pixel, but we can do this at every 20 pixels. So we can have a rough representation. And we start to see that vision is also not taking at high resolution processing. It takes these big receptive fields. But it takes a lot of measurements from these receptive fields. And with very many overlapping coarse receptive fields, you probably can do much better than the fine detection that we do now today. So we have these gradients, histogram of gradient patterns. And now it turns out if you take the average histogram of gradient representation of a face, it looks like this. You can easily find it because dot pattern matching is very cheap. If you say I have a certain pattern of, let's say, dots with some small properties, with these tiny orientations, you can easily do this. So you do a kind of a convolution, not with pixels, but with these oriented gradients. So you can find this quite easily and fast, and that's exactly what these simple hardware is doing. So now you find the rough area of where the face is, and you have a bounding box. And we find the bounding box in both of these faces. But now we are only step one. We only find where's the face, but not what's the face. So we need to find now characteristics, features that describe the face in a deep learning contextual way. So first of all, we have to look at can we manage the pose? And the pose means the 3D orientation. How would you do this? You want to make the faces in such a way similar that you say, okay, I can compare them. Because here, yeah, there's a lot of geometric transformations. The distance between the eyes is different. So we need to have some... And a transformation, suppose you have a plane. And if I have a transformation that goes like this, you have different projections. If I transform coordinates from this to this, it's called an affine transformation. The simplest transformation of all. It's a matrix of constants, A, B, C, D. You remember from the affine matrix from the angle. It's the same affine transformation. So if I find an affine transformation from this face, I can make it forward-looking again. But first, you need to find landmarks on the face to find the points on which the transformation can work. Because the transformation is a matrix, and then need to transform an old coordinate into a new coordinate. So it first needs coordinates of points. And people use 68 specific points, they're called landmarks, and that exist on every face. And people have different ways of finding these landmarks. So, first of all, people take the contour of the face and divide the contour in 15 equally distant points. So you have these points. We have points where we have high curvature. We have points where we have branching. So these landmark points, and tomorrow I go tell you in detail how the multi-scale structure of images gives you wonderful these landmark points. You all know them from computer vision. They are called SIFT and SURF, these famous key points or key point detectors. I can explain how they work. But these are these SIFT and key point detection. In Mathematica, we have a command that's called key point. Yes?
But if you have an image completely from the side of the face, like not all these points exist.
It doesn't work so well. If you see me like this, you cannot immediately tell it's Bart. It works better than, yeah, there's a kind of a, if I see my, from the back, it's completely impossible, of course. So it goes, let's say, up to, I don't know, 70, 80 degrees, and then it becomes more and more difficult. So we have these points, and now we train a machine learning algorithm to find these 68 points on the face. And here we have these points, and we connect them with these lines. So we have the jaw outline, nose, mouth, eyes. And then we have affine transformations. And what does an affine transformation do? The diagonal terms are the zooming terms. So the first one is how much you zoom x, and then how much you zoom y. The off-diagonal are the shear terms. So that means you have a, if I move it in this direction, then my square sheet of paper becomes a sheared piece of paper. So we have these affine transformations. You can look it up in Wikipedia if you want to see how they work, but it's actually a linear, constant transformation. And then this face, we have these landmarks detected. You find the affine transformation that the whole thing is frontal, exactly symmetrical. And then you find the face here, and this is now with the center in the middle. And you see this face, the eyes were here oblique, they're now horizontal. So it is not exactly horizontal, but you have now a rectified face. You can download the code for these landmarks, and it's on the GitHub from the author of this paper, and you nicely can do this yourself. Now, we need to find which face is it. So can we find specific properties in this face to find it? And we need to be able to recognize faces in in milliseconds, because Facebook has an enormous amount of pictures, and that's in the order of billions. So if you want to see who is this, are you going to compare to a billion of pictures? But Facebook is doing it. So how is Facebook doing it? You have to be clever to make this shorter. Who can think of a very clever way to compare a certain face to a billion faces? You have to reduce the search space tremendously. So let's see. What they do is they train a neural network, and at the output, they get 128 numbers at the output. So they have an output classifier. This is the MNIST classifier that gives just 10 outputs. But they say now we make 128 outputs, but they don't know what these outputs are. They just train the whole network and said we have 128 probabilities of something. We don't know what is something, but we get 128 numbers. And then how do you train this network? Well, they need to find an error, and they say, okay, let's look at 3 faces at a time. You load the training phase of a known person, you load another picture of the same known person, and you load the picture of a totally different person. And now you know what to minimize. The 2 pictures from the same person, they should be identical. So then you have these 128 factors, and you take the cross entropy, that should be minimal. But the picture with another person, that should be maximal. So you optimize actually 2 ways. You make the error with picture of the same person minimal, and you make the error with another person, make it maximal. That turns out a very nice training way. So you tweak it on 2 sides. And then, so you have these 2 images, you have these 3 images here, you compare the results, and if they are the same person, but different pictures, you get a minimum error, and if they are different persons, you maximize it. Well, this takes a long time. You have to learn this, and this takes forever, but people have done this, and this trained network is now quite valuable. Because if you now you use the trained network and you give it a face, you got 128 measurements. Nobody knows what these measurements are, but these are 128 very specific numbers for your face. So if I now compare now, and I have this done for every face, so for every 1 billion images in my Facebook database, I only have to compare 128 numbers of my incoming face with these sets of 128 of all the other faces. Well, that is going much faster. So we have no idea what these numbers mean. But now you have a very nice way of finding, it's actually a 128-dimensional feature space. And you have little clusters of where a face is. And now you need to find a very simple, ordinary classifier. I have 128 numbers. Where is it in this feature space? And a very famous and highly robust and well-performing classifier is support vector machine. Is anybody using support vector machines? You have heard about it? It's one of the most famous classifiers. I can really invite you, read on Wikipedia how it works. You have a couple of points, another couple of points. These are healthy, these are sick. How can you find the best separating line? And it's an optimization strategy. So you're going to move this line a little bit and see what happens. And then you minimize the error that it could be wrong on this side and wrong on that side. So it is a very nice mathematical construct on learning what it does. Then you say, okay, I don't have a singular linear line, but I may have a more complex line, I have a parabola, or have some other things. You can update this. But support vector machines do very well. So now you classify, and we classified it here with the embeddings of about 20 pictures from this first guy, Will Terrell, a completely different one, and Jimmy Fallon. And here you see the images detected during a late-night show in the United States. And you see the images were detected real time with pretty high probabilities. 85 to 95%. And even if these guys were very similar, and during the show they were making jokes of I'm him and I'm him, and it works. So I think it ends here. It gives a little bit an insight on how face recognition is working. A couple of steps. First, localize the face. Find the bounding box. You do this with histogram of gradients. Histogram of gradients are very special pixels that are actually not pixels, but locally attached stars to the local structure. You get the gradient structure, independent of intensity. They stuck to the image itself. Then you find landmarks on the image. Outline, eyes, these are the key points. And next week we go study what is SIFT and SURF and multi-scale key points. How can you build a very robust detector? From these key points you have coordinates, but you need to change these coordinates with an affine mapping into straightforward coordinates, so you look right from the front. Then you train the system, learn 128 properties, and that could be all kind of properties, so give me lots of faces and what are the 128 descriptors. People could also have thought, take 256 or take 1,000. And people may have done that, but it turns out with 128 you can already do this incredible, nice face recognition. So the cheaper the better, because it's easier to calculate. And at the end you have a classification, and you take any good working classifier. And there are, if you look at classifier in Wikipedia, you find dozens of them. Many students, they say, well, I don't know what classifier to take, so run them all and take the best. It's a little bit heuristics that many people do. But support vector machine is really well understood. And it works very well. And you see the result. Okay, let's take a break. And we see each other in 15 minutes. And we go talk about time and motion. See you then.